This is the video lesson for Section 5-3 in John Allison's statistics class at Pulaski Technical College. Recall that in Section 5-2 we found probabilities that a normally distributed random variable x took on a value in a given interval. For instance, if we had a normally distributed random variable x with a mean of 15 and a standard deviation of 2, that could be represented by this normal curve, bell-shaped curve, centered at the mean, one standard deviation, is 2. And if we wanted to know the probability that our random variable x took on the values, a value between 14 and 16, we could use the calculator and do second vars, go to the normal CDF, type in lower bound for our random variable x, upper bound for our random variable x, the mean for our random variable x, and the standard deviation for our random variable x, and the calculator would give us that probability. In this case, 0.3829 or 38.29% is the probability that this random variable x would take on the values between 14 and 16. Recall also, because the total area under the normal curve is 1, that this probability corresponded to the area under the curve for the interval x between 14 and 16. In section 5.3, we're going to learn to find values on the x-axis for a normally distributed random variable x when given certain probabilities. For instance, if we were given a random variable x that's normally distributed, and given the mean, and we wanted to find, we were given the probability that x is greater than or equal to a certain value a. Let's say the probability that x is greater than or equal to a is equal to 15%. We'll be able to use what we learned today to know that this area is 15% or 0.15, and we'll be able to figure out what that variable a is. Before we get started on that, we're going to start by recalling what a percentile is and a quartile. When we talk about the nth percentile, we're going to denote that capital P sub n, and that is the value where n% of data lies below P sub n. Recall, quartiles divide a data set up into 4 equal-sized parts. The first quartile, or Q1, is the value x such that 25% of the data is less than Q1. The second quartile is the x such that 50% of data is less than Q2. The third quartile is X, such that 75% of data is less than Q3. In these cases, because we're talking about a normal distribution, Q1 would be the value on the x-axis where the area under the curve to the left of Q1 was 0.25. Q2 would be the value on the curve where the area to the left of Q2 is 0.5. And because of the symmetry of the normal curve, Q2 is always going to be equal to the mean. Q3 would be the value on the x-axis where the area under the normal curve is equal to 0.75. As far as percentiles go, for a normal curve, the 60th percentile, or P60, would be the value on the x-axis where the area under the curve to the left of P60 is equal to 0.60, or 60%. We're going to start looking at the standard normal distribution, which, if you recall, has mean 0, standard deviation 1, and if we were given the probability, or given the area under the curve, in the standard normal distribution, the x values are z-scores. So if we want to find z such that the area under the curve to the left of z is 0.8, we're looking for the z to the right of the mean. The area under the curve is 0.8, which means the probability of any other z-score being less than or equal to this z is 80%. To find that, we're going to go back to the calculator. We're going to do second vars to get our distribution. This time you're going to go to number 3, inverse norm. Hit enter. What you'll see in the calculator is inverse norm, open parentheses. To find a z-score, all you have to do is enter the area that you're looking for to the left of the z. In this case, 0.8. Here, the calculator gives us a z-score of 0.8416. If we want to find the z-score where the area to the right is 75% or 0.75. Remember that the area under the total area under the curve is equal to 1, so that means the area to the left of z is 0.25. So in this case, we will do inverse norm 0.25. And we will see the z-score that corresponds to that is negative 0.6744. If you can find the z-scores that correspond to the given areas under the curve, the given probabilities, then you're also given the mean and the standard deviation of the distribution. You can convert those z-scores into actual x values. Let's say that for the distribution given above, we were finding the z-scores. Let's say that the mean for that distribution is equal to 50 and the standard deviation is equal to 5. We'll recall that the formula for z-scores is given by z equals x minus the mean divided by the standard deviation, and if we multiply both sides of that equation by sigma, or the standard deviation, we get z times sigma is equal to x minus the mean. If we add the mean to both sides, add mu to both sides, we see that mu plus z times the standard deviation is equal to x. So in the first case, when we found z equal 0.8416, if we want to convert that to an x value for this distribution, then we would say x is equal to the mean of 50 plus z 0.8416 times our standard deviation of 5. Type that in your calculator. And you'll see that x equals 54.208. In the second value, the z, where we find the z-score, negative 0.6744, we can say x is equal to our mean of 50 plus our z-score, negative 0.6744 times standard deviation of 5. And we see that this x value is 46.628. Your calculator can also, using this inverse norm function, find the value of a random variable x without first finding z-scores. Let's look at the same normal distribution with mu 50, standard deviation 5, and let's find the 60th percentile. Recall the 60th percentile in a normal distribution is the x value where 60% of the data, 60% of the area under the curve, falls to the left. So to find that, we're going to do inverse norm. This time, you're going to put 0.6, that's the area, 60%, 0.60, your mean, 50, and your standard deviation, 5. This is your area, your mean, and your standard deviation. The area to the left your mean, and your standard deviation. We type that in the calculator, and we say the 60th percentile is 51.2667. Let's find Q1, or the first quartile. Recall, the first quartile is the x value where the area to the left under the curve is 0.25. So here we're going to do inverse norm. 0.25 is the area we're looking for. Our mean is still 50. Our standard deviation is still 5. We type that in the calculator. Second, vars, inverse norm, 0.25, comma, 50, comma, 5, enter, and we see the value for Q1, 46.6275. Q2, recall we said is the mean, but Q2, let's verify that, is the point on the curve where the area to the left under the curve is equal to 0.5. So we should get 50, which is our mean for this distribution. Our area is 0.5, our mean is 50, our standard deviation is 5. Second vars, inverse norm, 0.5, comma 50, comma 5, and we get exactly what we expected to get, 50. Our Q2 is 50. Q3, the third quartile, is going to be the x value. 75% of the area under the curve lies to the left. So in this case, inverse norm, the area is going to be 0.75. Mean still 50, standard deviation still 5. Type that in the calculator, second vars, inverse norm, 0.75, comma 50, comma 5. And we'll see that x value is 53.372. 53.3724. Let's do another example. And let's find the z value in standard normal distribution such that the area between negative z and z is 70%. This is a little more tricky, but the first thing we have to recall is the symmetry of the normal curve. So we're looking for z where the area in between z and negative z is 70%. The symmetry of the curve tells us that these two areas are equal. The area to the right of z and to the left of negative z are equal because of the symmetry. Even though this doesn't look symmetric, it's because I'm not a perfect artist. We also know that the total area under the curve is 1. So if the blue area under the curve is 0.7, that means the green area under the curve has to be 0.3 because 0.7 plus 0.3 equals 1. If those two green areas are equal, then we have to divide 0.3 by 2 and see that each one is 0.15. So if we want to know the value z, we're looking for the value where the area to the left of z under the curve is going to be 0.7 plus 0.15 or 0.85. So to find z, we're going to do second vars, inverse norm. Because this is a standard normal curve and we're looking for a z value, all we have to put in is the area we're looking for to the left, inverse norm 0.85. And we get z equals 1.0364. Let's say we're working with a normal distribution where the mean is 136 and the standard deviation is 14. We want to know the value A such that the probability that x is greater than or equal to A is equal to 15% or 0.15. We know that this is a normal distribution, so we know that the total area under the curve is 1. So what we're really looking for if this area is 0.15, the area to the left is 0.85 because 1 minus 0.15 is 0.85. So we have A is equal to inverse norm. Our area to the left is 0.85. Our mean is 136. Our standard deviation is 14. We type that in the calculator, second vars, inverse norm, 0.85, 136, 14. And we find A is equal to 150.51.